Let's try another example of separation of variables. We're going to find an explicit solution, meaning we're going to solve for y at the end of the problem. And here's our differential equation. So first thing we want to do is get the variables separated, meaning we want to group all of the x's with the dx term, and we want to group all the y's with the dy term. So we could do that over a couple of steps. First thing let's divide by y, just to get the y out of the dx term here. So we'd have 8x dx plus x squared plus 3 dy over y is equal to 0. Okay, so we're getting there, and then next thing we'd want to do is divide through by x squared plus 3. So at this point, our variables are separated, and we can now go through and we can put an integral sign in front of each of these terms, meaning we're going to go through and we're going to integrate this expression term by term. Now before actually doing the integration, I like to ask myself whether we're ready to integrate. So if we look at the second term here, yep, that's a ln form, that's ready to integrate. When we integrate 0, we're going to get a constant, so that's good to go. And then looking at this first term here, this is almost ln form, and you've got a couple of options. So option 1 would be you could do substitution over on the side somewhere. You could work out the details of the substitution, and then you could just come back down and write your answer here. So that would be one way to do it. But what I would recommend is that you understand the shortcut that we discussed previously, and that we're able to use that shortcut to perform the integration. So I'm going to write one more step here just to get that first integral really ready to go. X squared plus 3 is the quantity that we've got in the denominator. What we'd love to have in the numerator is 2x dx, but in order to make this expression equal to that expression, we actually need to have 4 times 2x. So we're splitting that 8 up into a 4 times 2. The reason why we're doing that is so that we've got the correct differential on top. So now that integral is ready to go, and I'm just going to recopy the rest of that line. Okay, so here we go with our integration. We're going to get 4 times ln of x squared plus 3 plus ln y equals, and on the right side, when we integrate 0, we get a constant, so I'm going to call that C1. Notice that we don't necessarily need a differential on here. We don't necessarily need it to say 0 dx or 0 dy. No matter what our variable of integration is, we're going to get a constant when we integrate 0. So 3 quick comments here. Remember from our previous example that you only need one constant of integration on the right side. You do not need any constants on the left side. Second comment, remember that we're omitting the absolute values on the ln. So we're getting ln round brackets x squared plus 3. We're not getting absolute values in here. And similarly in the ln y, we didn't need absolute values around the y there. And then final comment is that if the question were asking for an implicit solution, then we could stop here. But remember that the question is asking us for an explicit solution, so we do have to do some extra algebra here to solve for y. At this point, the calculus is done, but we need to do some algebra. So first thing let's use the power rule for ln on that first term there. The 4 is going to come from in front of the ln, and it's going to become an exponent on the x squared plus 3. So we've now got ln of x squared plus 3 raised to the 4th power plus ln y equals c1. Good. Next step, we're going to use the product rule for ln. So since we've got a sum of two ln terms, we can combine them into a single ln, and what's going to be happening inside that ln is we're going to have multiplication. So we've got ln of x squared plus 3 to the 4th times y equals c1. Okay, and what that has allowed us to do is to reduce the problem to a single ln. Now instead of having two ln expressions in the equation here, we've just got a single ln in the equation. So what we want to do at this point is we'll say if the left side and the right side are equal, then e to the left side must equal e to the right side. So we're going to go e to the left side equals e to the right side. And e and ln are inverse functions, so these guys are going to undo each other, and what we're going to have on the left side then is just that quantity in the brackets. We're just going to have x squared plus 3 raised to the 4th power times y equals e to the c1. Okay, so now at this point we're very close to solving for y. Before we do our final step, I would just have a little discussion here about the constants. So if c1 is a constant, then e to the c1 is also just a real number, and typically we would rename this just to keep things simpler. So rather than calling it e to the c1, we would call it either c2 or c. Okay, the only thing that you really shouldn't call it at this point, you should not call it c1. c1 is not equal to e to the c1. So unfortunately c1 is not a valid name for that, but c2 or c, or even if you want to get creative, I guess you could call it a or b or something like that, but c2 or c would be the most conventional names there. Okay, so let's call it c. We haven't used the quantity c yet in the problem, so c would be a great choice. And then for our final answer, we would say y equals c over x squared plus 3 raised to the 4th power. So we have not only solved our DE, this was our solution back here, but we've actually found an explicit solution where we've solved for y. Thanks for watching, and we'll see you in the next video.